Hi, so in this video, we will study what is kinematics of particles and rectilinear motion as one type of the particle performing different types of motion. So what is kinematics of particles? Here, we are determining the speed of the car. So kinematics of particles is the analysis of a moving particle without consideration of motion. In this example, we do not consider the frictional force which is responsible for the car's motion. And here are the basic terminologies we have to learn before going into the types of motion. First, motion, particles, position, displacement, distance, average speed, average velocity, and acceleration. Consider a car which is moving at different points. The motion of the car represents the continual change in an object position. These points determine the position of the car. Particles are like objects that have mass but infinitesimal in size. If the car starts its journey from point 3 to point 4, then moves to point 1, then the total displacement of a particle is from point 3 to point 1. Displacement is the change in position of a particle. It has no relation with the actual distance traveled, whereas for the distance, it is the total distance traveled by the car. Average velocity is the particle change in displacement divided by the change in time. Average speed is the total distance traveled divided by the total time interval required to travel that distance. And acceleration is the change in velocity with respect to time. And now let's tackle about rectilinear motion. So rectilinear motion is the motion of a particle in a straight line, like this car traveling in a straight path. Rectilinear motion is divided into three motions. First, motion with uniform velocity. Second, motion with uniform acceleration. And the third, motion with variable acceleration. So what is uniform velocity? Bags moving on a conveyor belt moves at a uniform rate. The bags are considered as particles. Therefore, if the particles move with a constant velocity throughout the motion, then the particles is said to have a uniform velocity motion. When a particle is moving a uniform velocity motion, that is, its velocity is uniform throughout the period of the time, then its acceleration is zero. So what is uniform accelerated motion and variable accelerated motion? Uniform accelerated motion writes initial condition of particle, while variable accelerated motion takes the derivative of the given equation and solves the equation by mathematical rules. For uniform acceleration motion, we use the formulas V is equals to d over t, V is equals to v naught plus at, d is equals to v naught t plus 1/2 at squared, and v squared is equals to v naught squared or 2as, where d is distance, v is velocity, v naught is initial velocity, a is acceleration, t is time, and g is acceleration due to gravity, which is 9.81 meter per second squared and is also equals to 32.2 feet per second squared.
Sample problems. Problem number 1. A car is driving along a straight road at 70 miles per hour. The driver suddenly applies the brake, decelerating the car at a rate of negative square root of s feet per second squared, where s is in feet. What is the stopping distance of the car? This is a rectilinear problem for a particle in the sense that the car is traveling in a straight line. The given values are the initial velocity of the car, which is 70 miles per hour. We need to convert miles per hour to feet per second since the given unit for the acceleration is in feet per second squared. We can recall that 1 mile per hour is equal to 1.467 feet per second. So multiplying 70 miles per hour to 1.467 feet per second over 1 mile per hour, we will get 102.69 feet per second. The final velocity of the car is 0. It is because the implication of finding the stopping distance is that the final velocity of the car is 0. And acceleration is equal to negative square root of s feet per second squared. A negative sign indicates the deceleration of the car. The required value for this problem is the stopping distance of the car or the final position of the car. The equations for this problem are v is equal to ds over dt, or velocity is equal to the derivative of distance over the derivative of time. A is equal to dv over dt, or acceleration is equal to the derivative of velocity over the derivative of time. We can recall that the given are acceleration as the function of s, initial and final velocity, and we're trying to find the stopping distance. Relating the given values in the unknown, we will get the equation ADS is equal to VdV, or acceleration derivative of distance is equal to the velocity derivative of velocity. It has acceleration, velocity, and the distance which we're trying to find. To better understand this problem, here's an illustration. We have a car which is traveling along a straight road at an initial velocity of 102.69 feet per second. When the driver applies the brake, the car decelerates at a rate of negative square root of s feet per second squared. Then the car eventually came to rest, which means the final velocity is 0. We want to know the stopping distance of the car, and we can say that the initial position is 0, and the final position is what we're trying to find. For the solution, we have ADS is equal to VdV. Looking at this equation, we have a differential element s, which s is we're trying to find. In order to get the final position, we need to add up all the differential equation by integration. Substituting the value of acceleration, we get integral of negative square root of s ds equals integral of v dv. Substitute the limits of integration. The upper limit of the left equation is s, which we're trying to solve. The lower limit is the initial position, which is 0. On the right equation, the upper limit is the final velocity, which is v, and the lower limit is the initial velocity, which is equal to 102.69. Integrating the equation on the left, we get negative 2/3 s raised to 3/2, and we evaluate it between s and 0. Integrating the equation at the right, we get 1/2 v squared, and then we evaluate it between the limits v and 102.69. By substituting the values of limits, we get negative 2/3 s raised to 3/2 minus 0 equals 1/2 v squared minus 1/2 102.69 squared. By transposition, we get the value of s, which is equal to negative 3/2 times 1/2 times the quantity of v squared minus 102.69 squared raised to 2/3. We multiply the reciprocal of the exponent 3/2, which is 2/3 to both sides, to cancel out the exponent in s. And since the s is what we're trying to find, we can say that s is the final position or the stopping distance, and v equals the final velocity. And since the final velocity is equal to 0, we cancel out b sub f squared in this equation. So the final position is equal to negative 3/4 multiplied by negative 102.69 squared raised to 2/3. By calculating this equation, we get 396.96 feet which is the value of the final position and also the value of the stopping distance. Therefore, the final answer is 396.96 feet, which is our stopping distance.
Problem 2. In a boat race, boat A is leading boat B by 60 meters at a constant speed of 53 meters per second. At t equals to 0, the boats accelerate at constant rates, knowing that when B passes A, t equals to 9 seconds, and VFA equals to 67 meters per second. Determine the acceleration of both A and both B. The given values for this problem are time, which equals to 9 seconds, distance from both A to both B, which is 60 meters. Both A and both B have same initial velocity of 53 meters per second and a final velocity of both A, which is 67 meters per second. The values we're trying to find are the acceleration of both A and both B. The equations for this problem are Vf equals to Vi plus At and S equals to S of A to B plus Vit plus 1 half At squared. To better understand this problem, here is an illustration. At first, both A is leading both B at 60 meters. That is at t equals to 0. At t equals to 9 seconds, both A and both B have the same position. To solve for this problem, first we solve for the acceleration of both A using the formula Vf equals to Vi plus At. Divide both sides by t to cancel out t at the left side and get the formula A equals to Vf minus Vi over t. Substitute the values, so acceleration of A equals to 67 meters per second minus 53 meters per second over 9 seconds, and the answer is 1.556 meters per second squared, which is the acceleration of both A. To solve for the acceleration of both B, we use the formula S is equals to S of A to B plus VIT plus 1 half AT squared, where S equals to the final position. We recall that at t equals to 0, both A is leading both B at 60 meters, and at t equals to 9 seconds, both A and both B have the same position. We equate the final position of both A and both B. We get the equation S of A to B plus VIAT plus 1 half A of A t squared is equals to S of A to B plus VIBT plus 1 half ABT squared. By substituting the values, we get 60, which is head start of both A, plus 53 multiplied by 9 plus 1 half multiplied by 1.556 multiplied by 9 squared equals to 0, since both B came from initial position, plus 53 multiplied by 9 plus 1 half multiplied by AB multiplied by 9 squared. By numerical method, we get the answer for acceleration of both B, which is 3.037 meters per second squared. Therefore, acceleration of both A is 1.556 meters per second squared, and the acceleration of both B 3.3037 meters per second squared.